Great. Great.
Hi, Haris. It's so good to have you back again.
Hello, Karen. It's very nice to see you again.
Really looking forward to this, and we're doing this today. This is Haris's third time, I believe, on the meaning code, because after your second appearance, there were a few, let's say, challenges in the comments, and I made you aware of them, and you gave me a very thorough response to them, and I thought it would be a good idea to have that opportunity to give that response to the commenters as well. So one of the things that you said in the email to me that really interested me was that you said that what this proof establishes from the very beginning is that a rather obscure hierarchical ordering of the scientific method that allows room for construction and abduction. And that word abduction ran a flag in my head. I remembered reading about that some time ago when I was trying to study C.S. Peirce and his work. And so I tried to refresh my memory a little bit about C.S. Peirce, and he said that many times people tried to accuse him of using abduction as in the context of justification, justifying a theory after it has been developed. But C.S. Peirce said, no, abduction has its place in the context of discovery. It's the process of forming explanatory hypotheses, and it's the only logical operation which introduces any new idea. And so I'm interested to hear how you used abduction in the development of your theory. And also, you mentioned the speed of light as something that you were going to talk about, plus these two challenges in the comments. One had to do with circular reasoning, and the other one had to do with the fundamental nature of three. So,
yes.
We have a lot of ground to cover today, and I'm eager to see what you want to do. I've already set up share screen for you.
Okay, that's great. Just want to, okay. Wait a second. Just give me a quick second, please.
Sure.
Okay. Just to clarify something about what you said about this third method of reasoning that is called abduction. It is defined as a syllogism in which the major premise is evident, but the minor premise and therefore the conclusion only probable. So how they usually refer to it is like evidence to the we find it infers to the best explanation. This is what I was looking for. Okay. So allow me first to also share screen and okay. Can you enable the share screen?
That's right. We redid this. Sorry, I forgot that this is our second Zoom call today. So now it should work.
Okay, perfect. Okay, so no further ado, let me first try to tackle as many things I can. I will start first of all with this abductive reasoning and why it's not circular, my method of choice. And I will be reading from the email that I've sent you, but I will also be making some more clarifications as necessary. So in my defense against the logical fallacy that is known as circular reasoning, I will be utilizing mathematics, which is appropriate since we are talking about mathematics, and more specifically, Rademacher's modification of the contour. This is a modification that is made on the special case of the Hardy, Ramanujan, Littlewood circle method, and it's a technique that is widely used in analytic number theory. So just a few, one sentence, let's say a few words on the background. Rademacher discovered a modification of the contour that makes the series arising from the circle method converge to the exact result. So to describe his contour, it is convenient to replace the unit circle by the upper half plane by making the following substitution. Z equals to exponential 2 pi I and tau times tau, so that the contour integral becomes an integral from tau equals to I up to tau equals to 1 plus I. This is a nice modification that allows the formation of what is called force circles that we're seeing in the illustration here. So Rademacher's contour is more or less given by the boundaries of all the force circles arising from 0 to 1, exactly as shown here. So here's also the source from Wikipedia. Now, what is interesting here is that I can utilize this illustration to actually show the process that I followed. And what I mean by this, note that as each of the m values that arises out of the twin primality M tape, which basically it was a septuplet, so it had 7 values. Let me just show it quickly so we can remember it. So yeah, this one is for the master group, and the first M tape arising out of our total Turing machine is delivers these 7 M values, as we said in the previous episodes. So now, as each of the M values that arises out of this twin primalities M tape that was performed, the primality sieve that was performed on OA sequence A0020 2822, it corresponds to one of the 7 foregrounded force circles illustrated in this diagram. And most importantly, what I would like to note is that not only we can see the actual circles indicating each of the M values that arises, but most importantly, we can also notice these 2 small points here. Maybe it's better to show it here. Yeah. So we can also see these 2 points of the circle right here, which are somehow hidden. We can see that they exist on the 2/5 of the way from 0 to 1, and respectively to the 3/5 of the way. So what I can do now, I can actually use this modification of Rademacher of the contour to actually show you the M tape. Of course, it's also nice that it is this M tape actually corresponds to the size of the M values up to the symmetry breaking point. So up to here, exactly. So this is number 2, that's the first one. This is 3, the second M value. The third value is 5. This is 7, the big one. And then as symmetry breaks, we expect to find the 3 next, let's say, M values, having in this case, because this is the metric we use, the visual metric we use, to have exactly the same size from the first 3. So this is M5, this is 17, 23 is M6, and M7 is 47. Now, what is also interesting is that these 2 hidden small spheres that they have, I also noticed that they have the same size with M1 right here. They actually represent the breaking points of symmetry. This is the breaking point for the baby monster, which breaks at the 3rd primordial, which is 30, 2 times 3 times 5. And this is the breaking point for the monster, which is the 4th primordial, which is the previous one times 7. So it's 210. Now, just to, because I understand that it has to do with circles, so I sympathize with the view that someone might think that this is circular reasoning, but actually I can use it's nice that I can use the circle method of Ramanujan and Littlewood to show my case. And how I am going to do this, I'm going to show you the path that I've used in my abductive reasoning. So the path actually goes from here. It goes up, it follows the tangent, it reaches this point, and then it goes down until symmetry breaks. And you can see this first value, if you remember, is 2. So from the original sequence that we started with the m values that corresponds to the twin prime pairs, we skewed something, some values, specifically number 1. We left that behind. So we can also witness this here. And the same thing when symmetry breaks on the other side, we can see it also on this right hand side. And what I find that it's very it's a nice way to illustrate what abductive reasoning is, because I am sure if Pierce was around, he was going to appreciate this diagram of the pathway, let's say. So yeah, this is my main reason why my proof it follows this third method that is called abduction or retroduction. This is another word for it. So yeah, just embark to show that this actually corresponds to the exactly same size, and the same thing goes for the other circles that are from here. So yeah. Do you want me to say anything else about this, or do you think that I can proceed to the next part?
So, well, the last sentence there says that, so to sum up, the argument is not circular because it uses abduction or retroduction, and because it is also a constructive proof, where a constructive proof is a method of proof that demonstrates the existence of a mathematical object by creating or providing a method for creating the object.
Yeah,
and could you say just a little word about what that means?
Basically, what I wanted to clarify here is that since I'm using a direct construction proof, I am attacking the problem directly, so I'm trying to reconstruct the sequence that I want. In this case, the sequence under investigation was as we've seen before, it was the monster, and then we got, let's say, as a side effect, this spillover effect into the second largest member of the happy family. That is one of the 20, another one of the 20 finite simple groups that belongs to the 26 of the sporadics. And because it uses a construction and also an abduction, as it is, my proof is based on 3 steps. The first one has to do with this higher synthesis that actually reaches the limits of that Gödel proved with his incompleteness theorems, and in a way also Tarski. So to move beyond that, in order to complete the construction, we have to think beyond the machine. And the reason that I thought about it was like, if we go back to the Second World War, there were a lot of people, particularly women back then, that they used to be employed in the army and the intelligence services as what we call now human computers. And the only thing they needed to do was like to perform calculations, something like accounting, but even more, let's say, mechanical. So if all those human computers could do that like 80 years ago, why not try to do the same thing? So I believe that this is why I am particularly fond of not artificial intelligence per se, because I believe that artificial intelligence is a tool, but I am from a completely different school that comes from computational intelligence. And computational intelligence presupposes soft computing techniques like fuzzy logic and all the other things that I am dealing with. So it's much more, I am much more familiar with computation than artificiality, let's say. This is why I believe if we want to solve a problem that it's a hard problem, so what we need to tackle is this, how do you say, this property that such problems have, that we can define it in terms of one particular word that I call hard to subdueness. So we can take a problem that it's hard, or maybe it seems as if it's impossible to solve, and there is a special class within that really hard problems that they actually have a solution, and the solution that I am suggesting is to move beyond the limitations of the machine. So during the first step or the first stage of my this higher synthesis, I emulate, as I told you the other time, a total functional programming, or a total Turing machine that always behaves well, and I am taking these characteristics of the mechanical, let's say, and I am adopting them in my side, to the human side. So humans can learn from machines, and this allows me to go to the next stage, that is the analysis, and then finally to, in the case of the master, even to the total integration case. So it's more like what I said before, we are trying to make an inference to the best conclusion. So this is what abduction is. You use, and in my case, I use both construction and also abduction. So this is what I try to do. I was hearing a recent interview, a recent podcast from Professor Brian Keating, and in which he mentions that there is no, how he call it, the scientific method is not written in stone. So I agree with that view. And basically, what you mentioned when we started this episode, you said that what I mentioned the other time, that I am using this obscure reordering of the scientific method, that I believe it's even archaic, let's say, in an effort to arrive at the current state of the art and the current state of progress, let's say. And if what I am saying corresponds to the actual reality, then that means that, and now I'm trying to make a link with the great discussion that the 3Js had, Jordan Peterson, John Vervaeke, and Jonathan Pageau, regarding the difference between the nomological order and the narrative order. So for me, and I hope Professor Vervaeke will allow me to make this observation, I believe he's slightly on the wrong here, because what he suggested was like we should be tackling the union of the two, and I strongly disagree with that, and I will explain you why I disagree. Because I don't believe it's a union, I believe it's a division between the two. Why? Because if the nomological order, for one example, a nomological order applies to rules, okay? Rules that we all know and that work. So for example, in the nomological order, one such rule is that famous Einstein equation. Let's say that is the most famous equation in physics, E equals mc squared. So in my own narrative, because I am not let's say I'm not representing the nomological order here, I'm bringing something new. So I'm bringing my own narrative. In my own narrative, because P, as we are talking for the twin prime numbers, because we constructed this proof for that links, let's say, the twin primality with the monster group and the other groups that belong to the same class of groups of symmetries. What is necessary is to understand that I said that is equal EMC squared, where P minus Q equals C, and therefore C equals the event constant. That translates into my narrative into the energy being equal to 4m. Okay, so I have two things that they are equal right now. I have the nomological order that everything thinks and talks about that and uses it. And I have my own personal narrative. It may be wrong, maybe it's right. We will find out. I believe it's right, but everyone believes their own theory. Own theories are correct. So the reason I am sure that I am not sure. I am pretty sure that I am going into the correct path here is because when I take the EMC squared and I divide it by my result, I get exactly the unit. So it's a logos, it's like a ratio. So when they are talking about logos arising out of the nomological order and the narrative order, it's not you take two things and you put them together, because it's not the union. This is why where I disagree. Because if I take, for example, let's agree that m equals 2, for example. Okay, so EMC square will be in that particular case equal to 8. In my own case, it will also be equal to 8, let's say. But if I take these two and put them, either if I add them together, it means I will get two things that they are the same. If I multiply them together, I will get something else. So what I have to do is I have to show the logos, the ratio, where I have the actual formulas on the nominator, let's say, and on the denominator, I have my own narrative. So it's the nomological divided by the narrative. And if you get as the output of that ratio is equal to 1, then it seems that we are correct. So I wanted to just clarify that a bit. Now, I will move quickly into the next point here, that my method is also not circular because it follows quite literally a sequential yet effective method. I will explain what this means. Because we start from the first input sequence that belongs to the twin primality, and we arrive to the desired output, that in that case is the 50 super singular terms of the minimal order of the master. But let's go and see for a second what actually is this effective method of found in logic, mathematics, and computer science. And I would like to add also in computer adaptability theory and also in meta theory that covers meta logic and all of that. We can go also meta at some point with all of this, but still I believe we just need to do the basics. So allow me just to read from here. Effective, a method is formally called effective for a class of problems when it satisfies this criteria. So let's go through these bullet points and see if my demonstration of my method corresponds to these points. So it consists of a finite number of exact finite instructions. When it is applied to a problem from its class, in this case, the class is the happy family. So it gets applied to two problems from that class. That is actually the monster and the baby. And when it is applied to either one of them, it always terminates after a finite number of steps. We also have seen the metrics how these work with the floor of the half of the size. It always produces a correct answer. For me, this that it always produces correct answers have to do with abduction, because it's like you are playing this. There used to be back in the 90s, we used to have a game called Mastermind. where we were
I
trying
remember that, yeah.
that uses abduction. So I don't know if it was peers that developed that game, to be honest. So you are trying to, you are playing, how do you say, a detective. So you are trying to find the actual solution by looking all the information you have. As I said in the previous time, we know that the master exists because of the proofs of all those great mathematicians. And we know some other things like the size and the lower limit and the higher limit, that all of them are useful. Continuing, in principle, can be done by a human without any aids except writing materials. I think we have established this. And its instructions need only to be followed rigorously to succeed. In other words, it requires no ingenuity to succeed. What does that mean? It means that even though I'm claiming that my proof moves beyond the incompleteness theorem and the limits of computation, the computability theory, still, because I've managed to put it into words, let's say, and instructions, I can now refine the whole thing as an algorithm and give it to a PC, to a computer, in order to perform the actual thing by itself. This is what I mean, that it's an effective method.
So that was Turing's work, wasn't it? Wasn't he the one that came up with that definition of an effective method?
I'm not sure about that.
Well, it's not important. I was watching a video by Up and Adam this morning, and she was doing a history of the Turing method, and she talked about those 4 points. And so they're just top of mind right now. So
Okay.
so cool, very good. Okay, so that advances significantly our current understanding of the 15 supersingular terms of M.
And I can clarify that because what I mean by this is because when we go to the in Wikipedia, but also in the articles, in the scientific articles, we see that our current understanding is that the number that is responsible, let's say, for breaking this nice description that we have, that is actually, the description is verbatim. It's like the current state of our understanding states that the master corresponds from the 11 first primes plus 4 exceptions, 41, 47, 59, and 71. What I am saying is that I am rectifying the number 37. And I'm saying that it wasn't 37 that it's in the wrong. Actually, it's the other non-singular, non-supersingular prime numbers. So it's not 37, but it's 43. So this is something else that I would like to add. This is the point here. It restores the truth of the matter as the first non-supersingular prime, namely number 37, is not responsible for symmetry breaking. It is rather 43. And just to go back, you see, sorry. So if this is M4 is 7, how I understand it is that not only when this symmetry, the first symmetry break, the big one, when it happens, it actually breaks, it opens up, and the M values indicate to the N value. So each M value indicates to a pair of Q's and P's that together as a product, they represent an N. So in this case here, if M4 is 7, that means that this guy here, it's this half circle here, it's Q3 and Q4, and this one is P4. So this is 41 and this is 43. So the break happens exactly here at 6M, which is 6 times 7, which is 42 again. So this is how I perceive it, because even if we go to the far end and we check the limit of the master, that is 71, still if we multiplied it by 2 and we add 1, we will discover the first 10, we will discover 143. So that's something else. It's like the n values indicate to these n values, also pictorially. And that's the second.
So could I just clarify that for a second? Go back to that picture. So maybe I have this wrong. Maybe you're just talking about ratios or something, but if M4 is 7 in diameter, then Q4 is 41 in diameter? Or
yes, you can say like basically these two as they represented here, I believe, because it's not an actual representation. It squashes things up a bit. It just allows us to see this thing right here. So if we put these next to each other, what I don't believe they are too different. They are like one is Q and one is P. Maybe this is 6M and this is 6M. So maybe something like this. We need to extend the Rademacher's contour even more to see the complete circles, but this is what my intuition suggests.
Okay. Be interesting to take a compass and see if it's correct.
We can do it. We can try.
Yeah.
We can try.
Okay.
You know,
well, I was just trying to clarify where the numbers came from.
Yeah,
So
as I told you the other time, it's nice to find this because actually the information we can get from this diagram it's unbelievable, because it gives us beautiful pieces of information. Like for example, it tells us that the distance between M3 and M5, which M3 is 5 and M5 is 17, which is 12, which 12 is our measure, because even if we go down to the imaginary unit where our M value equals the imaginary unit, we still discover this number 12, which is very fundamental in number theory. And it seems that it shows us that this distance as we see it here from 1/3 to 2/3 actually represents 12. So and we can even make other let's say clarifications. So the distance between 2/5 and 3/5, this is 30 and this is 210. So then this distance, the 1/5, is equals to 210, which is the fourth primordial, minus the third primordial, which is 30. So this is equal to 180. And when you calculate the whole thing, you notice that, okay, this is we're talking about 1/5 and 4/5. But when you see the whole thing together, you understand that actually this corresponds to the number 7. So when we add these two things right here, we will find another 2 units. So this actually can be cross-referenced with something that is called roots of unity. So the roots of unity of this thing is 7 is one of them. And this is another nice result because I also arrived to that, like 7 seems to be indeed the breaking point or the initial breaking point of the symmetry. Okay, so the other thing that I would like to add here is that it advances our understanding of the origins of the master. So not only this method that I propose, it's equal with the current understanding, but because it provides this additional pictorial representation, it allows us to see some other things. So what I've said here, Occam razors wins, and minimal leg theory always wins, and minimal message length theory always wins. So what I mean here, I can actually write a small line of poetry about the master group and the baby. And I can say that the master corresponds to the first 7 prime n values, 5 q's and 3 p's. And the baby master corresponds to the first 7 prime n values, a sole q and 3 p's. So again, when you actually look at this, this is true. Of course, it's not a lossless encoding as this one, but still it's something extra. Just to go to MML, and thanks to Chris Wallace, the Australian computer scientist and physicist, that he came up with this theory. This theory provides a formal information theory restatement of Occam's razor that says the following thing: even when models are equal in their measure of fit accuracy to the observed data, the one generating the most concise explanation, I underline explanation here, the explanation of data is more likely to be correct, where the explanation consists of the statement of the model followed by the lossless encoding of the data using the stated model. So just to show you, because this thing is actually quite dynamic, and yeah, what I wanted to show you here is the following thing. As I told you before, until in the first episode, I showed you how we can reconstruct the minimal order of the master, which is a member of the happy family. On the second episode, we've seen how we can also reconstruct based on the exact same method, but reversing the order of the analysis and skipping completely the total integration stage that is only applicable to the master. We also arrive to the minimal order of the baby as a bonus. And because this effective method is talking about solving classes of problems, what I offer here is the following. I can also represent Yankon group 3, J3. This Yankon group, it's not one of the 20 members of the happy family that belongs within the master group. Yankon group is one of the 6 pariahs, pariah groups. So, and I can show you why it is a pariah and it's not a member of the how do you say, the happy family. So the reason is this. First of all, let me go to Yankon group. Yankon group is here. So the Yankon group is much smaller. The actual size is 5. And as you can see, this is the full order of the thing. So it's way more manageable than the master and the baby. So again, by applying the same algorithm, we arrive at the 3 first n values. And then when we start performing, because now we know that the size of our analysis is actually the floor of half of the size. So it's 5 divided by 2. So the floor of that is 2. So expect to record only 2 values during the analysis stage. When we try to reconstruct the Yanko group, Yanko J3, in my pictorial view, let's say, in this pictorial view, what we have to do is the following. We place down M1, M2, and M3 that arise out of the M tape. We note down Q1 because it's the value of M1. Sorry. We note down P1, which is the value of M2. We proceed to the next one. And then we realize the following thing. In order to complete this, what we have to do is something different than what applies to the happy family. We need to remove this and we need to add another, go one step further by continuing. So this Yanko group, it's, as you can see, the shape is a bit like a Tetris. It goes a bit like this. So it can be represented in this order, let's say, and to be exactly correct and paying respect to the previous assignment, let's say, of Q's and P's that I followed, I've represented it in this way. So this is after we perform this removal of the excess values. In the case of the Yanko group, we have to remove 2, not only 1. So this is why it's a pariah. This is how understand it. And just to show that still we're within the sporadic family. But we can, sometimes there is another group that sometimes it is sometimes considered as the 27th sporadic group. For historic reasons, I think it's not included. So this group actually exists in the limit. It's a sporadic simple group, but because of historic reasons, it's not considered as part. And we can even go to this limit of what is a sporadic group. And as you can see, this one is represented by the minimal order is 2, 3, 5, and the first p-value. So it can be written like this. So even though this group that Jacques created does not belong officially into the same group as master and the baby, it still exhibits the same method for its construction. So it's, again, I don't have to break any rules to construct this. So this is how, again, it looks like these smaller groups looks a bit like a Tetris tiles, if you ask me. So yeah, I wanted to also share this with you. And in a way, we can extend this even further to the whole sporadic family. So we can have a full table that resembles, let's say, the periodic table found in chemistry. Yeah. Now, okay, so tell me if you want me to, if you have any questions, or if you want me to.
No, I think you've covered that well. I think I get it.
Great.
I mean, I think I get how you can use this. Well, I like the idea of using it to like create a periodic table of the group members, because what you're basically showing is the way in which they're all connected.
Yeah. It's like they are origins, that they are the twin prime values. So it was like that. So yeah, this completes the reply to that the argument is not circular. Basically, because we've initiated our journey to reconstruct them and ended up reconstructing more groups. So now I will go here to the I think I will go to the speed of light now, if it's okay. Yeah. Okay. So now, I really enjoyed this because I was trying to answer to you. I enjoyed all the questions, by the way, both from the audience.
It's really it's a little bit scary to me that I ask a simple question like that to me just seems like a question of curiosity, and then it required so much work on your part to answer it. So I have to apologize.
Don't. This
for
is
putting you to all this effort.
We're making history here. No worries. This is I really like this. So yeah, I would like to thank everyone, including you, for all of these very nice questions and critique. So I will explain to you what I mean. Let's say regarding the speed of light and how I came about it. Basically, to be honest, I wanted to say that when you asked me during the previous episode, about the m value or the t value for the speed of light, I knew the answer. But I knew the answer because I made the same question. I knew the answer for the approximation of the speed of light, that is 300, is this number here. It's 300 times 10 to the 6th. So I knew this about the approximation, which is okay. But I didn't, haven't completed the actual, I wasn't certain if it continues this value to be the same also for the precise speed of light. So I've done the calculations and it's the same, and it's very good that it's the same. So,
Well, okay, so just to recap, one of the concerns of one of the viewers was that these numbers for the speed of light are in meters per second. And since that's a unit, and units, so the number before the unit would differ based on what kind of unit you're using. So, but then you're using these numbers in a particular way as if they have a particular meaning. But what if you change the unit to feet per second or hours, or miles per second or something like that? Then your numbers would be different, but do you understand the question?
I understand, but listen, if you listen how I understand it. Let's say you are driving a car in United States and the car is in miles, right? You have miles there.
Mm-hmm.
When you come in Europe, and you rent a car, you will notice that we have everything in kilometers.
Mm-hmm.
So let's say that Karen always goes with the same speed limit, right? Whenever she drives, wherever, maybe US or Europe. So if that is the constant, then even though you are the dashboard of the car will record a different number, it doesn't mean that the speed is gonna be faster because your speed is constant, right? So if you want to keep a constant speed, it doesn't matter how the dashboard translates it. So one value is true both can be expressed in miles and can be expressed in light years or kilometers. So it's the same thing, it's just a conversion. It doesn't change anything. If I've used that base for, and I will explain to you why it doesn't matter, because we can start talking about dimensionless constants in a bit. So that I think removes all.
Okay, well, I just wanted to get that out there so that the viewer knows that we're looking at their comments. We always appreciate the comments.
Yeah, of course. So now, in the case of so first of all, allow me to explain to you my line of thinking. It was very simple. It went like this: whatever works for the approximation of a value should also work for the exact instantiation of that value as well. So that was my initial argument, and equipped with this thing that I knew about the approximation, I continue. So in the case of the value of the speed of light, it is well known that it is approximately equals this value right here, that is meter per second. Okay, so it's 300 millions meters per second. Now, this approximation, we can demonstrate also, we can represent also with this technique that I am using. So I am referring to speed of light. I write it down as CL because I believe that, first of all, I believe that I have altered a bit my view that the speed of light has many different speeds. For me, now the speed of light only has two speeds: the normal one, the fast, and the slow. Okay, C equals 2, and the full speed one, that is the one we know. So the full speed can be represented actually like this: C, which is 2, times L. So even Einstein, in his original paper, when he formulated the E equals mc squared, he used this L for a good reason. So this L is important. So we can refer to the speed of light as CL. Now,
Well, you have to explain one more thing to me. I know you explained this the first time around, but I didn't quite grasp it. Why are you positing that there are two speeds, the fast and slow? Because the only one I've ever heard about is the fast one. I've never heard about this slow speed of two.
Okay. Because when you imagine, it's a very simple thought experiment that I did. When you imagine the first light that came out, it came out and it got accelerated to the speed we know, right? But if we somehow manage to go steps frame by frame before to find the exact moment, let's say in time, where for the first time ever light emerged, that light didn't emerge at c squared. It emerged as something smaller, right? It emerged with the actual value of c, and then it got accelerated and all that. So because this value is equal to 299,792,458, when it started to go out, let's say as a value, the very first instance, it got instantiated as 2. So I'm not talking about, it's like, imagine taking a photograph and it's not like very good because you move a bit and you get that line, let's say. So it's something like this. It's something like, this is how I believe it emerged. It's like a baby, let's say. First you have the head and then you have the whole thing. So this is how I see it, because this light, and I can show you in the following episode, let's say, if we don't have time now, but I believe it arose, light was there even before the Big Bang. This is another strong statement, and it has to do with this smaller, let's say, slower speed. So this is my assumption. I'm not saying that I am fully correct. I'm just saying that if I go along with this, these results follow. So let's see what the community has to say about that.
Okay, so then let's go down to these symbols here. The CL, the C is 300 million meters per second, and then L is
basically, basically C is this, so CL is this, and L, it's 7 times 73 times the P, which is 9339. So this is
I see. You factored it, and then you just took the 2 out as the C.
Yeah,
and then the L as the rest of the factors.
Yeah, that's the light. So I'm just splitting it a bit. It's not that I'm doing something extreme here. And imagine that whatever I'm saying is correct because the speed of light is a constant. So many times in physics, they replace the whole thing with 1. The only thing I'm saying is like, instead of 1, don't do it 1, it's wrong. Replace it with 2. This is what I am suggesting. And because interesting things follow. So I can represent this CL, but I'm talking about the approximation now, with this formula for the total volume that also compacts distance. And this formula breaks down as 12 times m squared times n. I know that the m value for now answering your question, the m value for the speed of light is 5. So it's going to be, and the n value, the extended n value in this case, because we are talking about the full speed of light and not just the c value, it's equal to n equals 1 million. So it's 12 times the n value that is 5 squared times 1 million. And it gives us this value. That is equal to 300 million meters per second. This is the approximation. Now, as I told you, can we take it, this thing that we know that the value is equal to 5, and try to express the speed of light, the whole speed of light? Yes, we can. And how can we do it? By introducing two two terms. Now, I can explain this to you in the following manner. So my first initial correction term or approximational deviation term, it's negative. And the second one is positive. Now, how come I thought about this? Okay, this is, it comes from here. Okay. Sorry. No. Yeah, this one. Okay, so Einstein's general relativity equation, which is this part here, can also be stated like this. You see, the second term, the first term that he has to this one, it's negative, and then he just adds the cosmological constant. So it's a term, the approximation, this is how I understand it, minus the first error alleviation terms, plus the cosmological constant that you can also ignore. It's the only constant you can ignore in general relativity. But okay, so this is how I came up with this. Now, here how it goes. Yeah, I will focus on this line here. So it can be written in the following manner. This first term of the initial correction can be written as minus 2 times m to the cube times the square root of the extended n that we've used before for the approximation. So the n that we've used before was 1 million. So the square root of that is 1,000. Actually, when we do this, as you can see here, we started from a round number that is above our limit. We subtracted this value here that is 500 squared, which it's interesting because it's 100 m to the cube. So it's 100 times 5 squared. And the final correction term is this one. It's 12 times m squared, which again, where again m is equal to 5, minus 1, times c, which is the same c here, so it's 2, and q, where q is the number 71, which is the highest supersingular term of the monster, and where also 2 is the lowest. So this second final correction term to arrive at the correct and precise speed of light has to do with the monster. So again, it makes this link, which allows me to perform this type of calculation and derive both the approximate value and also the full value. In fact, what I'm saying here is that this term here can also be expressed in a different manner. It can also be calculated with this formula. So it's not that I thought about it only in one way. I thought about it from two completely different ways, and those two ways they came together. So this has to do with this is the frequency for the speed of light. So what I'm doing here is like I am using only, I am not even using in this case that extended n. I'm just using the values that my theory gives without even going and checking how large is the speed of light and what modification do I have to do? Nothing like that. I'm taking the full volume when m equals 5, which happens to be, I think I have it here, is 26,000. Oh, wait. Anyway, maybe I'm not having written down. So let me explain this. Yeah. So it's gonna be 12 times m squared, which is 300, times 899, that is the m of, that is the n value corresponding to m equals 5, divided by 3, times the frequency, that is c divided by n. All of this, again, multiplied, a small modification here. I'm just exchanging the 3 with the 2. Get this 9,000. Divided by 12 times t. So here comes the t. T equals 3 times m. It's 500. And because it's a negative term, what I can do is like I can introduce a third term on the nominator, which is the imaginary unit. Sorry. Yeah, erase that to the square power and again arrive at this 250,000, which is the first correction term. So yeah. Now, noise, go down. So yeah, alternative, it can be expressed like with just the negative sign without having to include the imaginary unit. And this actually, yeah, this actually goes down to this, which let's compute if it's the same. Sorry, this calculator does not allow me, so I have to do it here. Sorry. Apologies.
You're doing great. I mean, if I was sharing screen on this, I would be 5 minutes between every page.
Sometimes it doesn't work the copy actually on Outlook. So. Okay.
Use these calculators, you practically have to know how to be a programmer.
This is, you know, when I was programming, I was always, okay, I feel that my logic is quite reversed than most people, but when I was at university, the language that I was excellent at was assembly. And assembling is at the low level, let's say, computing language. And I was always thinking like, I wish I could, how do you say? I wish I could program in in machine code. So this is very close. It's like, for me, this is, it's the natural language of primes. It's a natural language that is also, it is also a formal language. So it's the only language that is what I call proper. It's both formal and natural. So you can do many things with this language, because then you can apply the pumping lemma, you can do a lot of things. So it's way more natural than we think. Not the language of the numbers, particularly the language of primality. So yeah, I have some mistakes with the brackets, but it's exactly the same value. So with this calculation, we arrive at the value that we want. And that's it. This completes the, let's say, my calculation for both the approximate and the precise speed of light. So to answer your question, the t value for the speed of light for both its approximation and its exact value, it's equal to 15, 3 times 5. Because the value of the speed of light is 5. So this 15 is important. It seems to be like we can utilize it for many other calculations, but also the m value that is equal to 5 for the speed of light. It's also important because equipped, as I wrote in my email, equipped now with this insight from calculating this value for the speed of light, where the n value is 5, n equals to 899, and the extended n value is equal to 1 million, we may proceed to approximate yet another constant found in physics, namely the fine structure constant A, that is also known as the Sommerfeld constant. And this, I believe it can be achieved in a quite relatively good accuracy. So now I'm trying to, I'm in the game of redefining constants, so that's a nice game. So fine structure constant, not redefining, recalculating. So yeah, this is the fine structure constant. This is the whole thing here. In my worldview, things are reversed, because whatever is very small, for the quantum, whatever is small for the quantum, it has to be large for the integers. So we humans, we can parse it. And the only thing I did here is that I remove everything else, even the reduced Planck constant. And the only thing I did, I inverted the e to the square power. So I did it like, I started from 1 and divided by e to the squared, e to the squared. So it was like, sorry, it was like this. So we get this value here. And from there, what I thought was the following. Again, I'm going back to my calculation formula. And I said that, okay, I will still get the total volume, and I can calculate it as before, which is the exact same calculation. It's this number here. I can use here this formula that uses only the m values to arrive to it. And then I can, when I take this full volume of the universe, as I call it, let's say it like that, when the value was 5, that is the value of the speed of light, and I utilize also the same extended n that I used to perform both the approximate and the precise calculation for the speed of light, which was 1 million. And then just multiply that by 1 divided by e squared. So what I arrive at, it's an approximation. that is equal to this value here. And this value here actually it's nice. It's a nice value. This is the correct one right here. So it makes the approximation up to the fifth decimal place. The approximation by itself, it's nice because no. No. Excuse me. Again, forgot to manually copy. Okay. This is the reverse. Okay. So okay. You see, this is actually quite good. It's a nice. It has a nice period. Let's say you have 3 continuous 7 here. You have 3 8s here. You have 3 9s. So you have 3 9s, 3 7s, 3 8s. This is not important. I'm just saying that I'm just making an observation that it has some nice, let's say, properties to it. But when I go and make second, yes, when I go and make when I go in and subtract my estimation for the Sommerfeld construct, for the fine structure construct, and the actual value, this is my error rate, which is very, very, very small. I think we can do physics with even less precision at some point, but that I was able to again use this simple formula that I've discovered, let's say, in order to come up with something like this. I also believe it has some interest, let's say, to the community, to the audience. So yeah.
Well, we've covered about everything we said we were going to cover, plus a little bit more. And my brain is getting fatigued at this point. So I think maybe we need to, try to wrap it up in a few minutes, if you could.
Yeah, I will not show. I have many things to show to you, but I will not go into more maths. I believe what we can, if you allow me, what I wanted to show to you was those 2 short videos that I've sent you. It's okay to see.
Oh, sure.
Yeah, it had to do with what Glenn said about the 2 different types of evolution that exist. One has to do with it's the Darwinian one, that it has to do with a random walk, and the other one it's the, let's say, the rule based, that it has to do with an intelligent walk. So
well, hold on just a second. Would that be something that would be related to what you've just shown us, or would that be kind of a new thing? Because we could start a new episode with that if it's a separate thing.
This was just like a small feedback that I wanted to give to Glenn.
Okay,
So that was
okay,
it. It's not that it's related to this. It's just I believe that because we are talking about this, even in my theory, we are seeing some evolution of these M values and all of that. That it is not how do you say? It's not exactly it's by natural selection because the prime M values they arise out of the natural order of the primes, but there is also something else that is going there. It's very short, these two videos, and I believe if
okay.
you want to wrap it up, we can do this. So it would be nice.
Σύμφωνα με τις έρευνες, 3 μερίδες ψάρια.
The first one has to do with cuckoo.
Just next door, in an even smaller nest, the female reed warbler incubates its 4 eggs. One of the brood is starting to hatch. However, it is not the young reed warbler. 2 weeks ago, a female cuckoo, unseen by the reed warbler, dropped her egg into this nest. Now the young cuckoo hatches. As the first of the brood, the reed warbler did not notice the trick, and now feeds the young as if it were its own. The young cuckoo needs to throw the other eggs out of the nest. If it doesn't do this, then the parents will not be able to feed all the nestlings. But the first attempts are not successful. The cuckoo is still too weak. It tries again. It must push the egg above the edge of the nest. It is a big effort. The determination of the weak cuckoo nestling to get rid of the competition is amazing to see. After a few hours, it has another go. This time, there's some success. The first egg landed in the water. When it throws out the second egg, the cuckoo almost follows it out of the nest itself. Now, for the last one. Alone, at last. The ever-open, bright red beak and the constant peeping from the cuckoo prompts the reed warblers to bring it food without a break. Now all the insects and spiders end up in its beak. With such intensive feeding, the young cuckoo reaches its adult size in just 2 weeks. It is so large that when it sits on the nest, it must hold tight so it doesn't fall off. In a strong wind, the nest may even break apart under its weight. Although the cuckoo is by now much bigger than the reed warblers, they still treat it as if it's one of their own nestlings. Even after it has left the nest, they will still feed it. At the end of August, the young cuckoo will start its lonely journey to Africa. It will return next spring, maybe even to the same reed bed, and try to toss an egg into a reed warbler's nest.
That's amazing.
For me, that is like, it's also amazing, and it's like it represents at least what the young cuckoo is doing. It represents the random walk. This is what I believe. And now I'm gonna show you something else, because nature it's amazing. I'm gonna show you the other one, that is the intelligence. This is, so yeah.
Wow.
Yeah, this is how I understand the random walk with the intelligence dance. So both exists in nature. It's not like, this is why I agree with Glenn. You can have both types of evolution and behavior. So yeah.
So how does that connect up with the narrative and the nomological?
Basically, what we have heard now, it's as if, I will explain to you how I understand it. It is as if we are going to a rugby game or whatever game, and we are watching the actual game unfold, and then you watch next to you, and you see one of the other fans. He's holding like his phone and listening to the narrator from the radio broadcasting. So some people, they prefer to like also, the narrator. It doesn't mean that without the narrator, the play is not going on, right? So I believe they are interpolated, the two. So you can either choose to just watch the one, or dig into it a bit more and get more information out of it at the same time. So it's two different channels, as I understand it.
So do you think that one of these walks represents one of those and one represents the other? Or
Yeah.
are these both narrative?
Both are narrative, but it doesn't mean that they don't correspond with they don't have a distinction. They have a distinction, because the first one, the young cuckoo, what he's performing is utterly, the work he's doing is random. He just pushes and tries to, you've seen it. But in the second case with the birds of paradise, and it's not only one species, it's many species, they orchestrate their moves in order to arrive to a different, let's say, conclusion. In both cases, the driver is evolution. Like in the case of the cuckoo, he wants to achieve that in order to survive, let's say.
But the thing I don't understand about the cuckoo example is, why doesn't the mama bird, why doesn't she go extinct? Because if all her young are being pushed out by cuckoo birds that have been dropped in the nest, then
yeah,
there'd only be one or two generations of that kind of bird, it would be over.
Yeah, but I believe it's this thing. It's called parasitic broodism, if I'm not mistaken. Actually, the two species, the warbler and the cuckoo, they are in synergy. So even though that the cuckoo does that parasitically, let's say, still it makes sense for the pair of the warblers to continue doing this thing, because it's something like it's a lottery. It's a chance that they have to take. If it was even more, let's say, aggressive, the cuckoos, maybe then they will change the behavior. But because they always laying eggs, maybe they like it. I don't know. Maybe they calculate it into the whole thing as it unfolds. So you can see these differences there. And in the case of I think this is a nice way to conclude. The other thing that I've sent you was regarding the Wortian case that had to do with with an innovation that came from the 19th century and had to do with it solved a particular type of problem, how they wanted to transport plants, exotic plants overseas. So one particular inventor, a doctor, he came up with the so-called Wortian case. That is a case made of glass, let's say. And he noticed there that when he created this case out of an accident, basically, he made some experiments, and then he showed it to some an admiral, and told him, let's try this. So they took the Wortian case, they sent some plants to the other side of the world, namely to Australia. They unpacked the plants survived until they went over there. And then the Australians, the botany center, basically, they used the same Wortian case, and they placed their exotic fairs, or whatever was the craze at the time, and they shipped them back. And when they arrived back to London, they were still alive. So before this invention, only 1 in 1,000 plants was able to make this long trip, let's say, because of the ocean spray. The ocean spray destroys plants, especially delicate plants. So because of that innovation, they managed to kickstart these logistics, let's say, of transporting live plants. Of course, it's interesting because when they started to do that thing, accidentally, they also introduced into the natural habitat some foreign insects. And it's a nice conclusion to the story of that particular invention, that is the Wortian case, because approximately 100 years later, they used that same case to solve the problem with the parasitic insects. And what they did is, like, they used the same case to send to that location that they introduced the problem with the parasitic insects. They sent them some bigger local wasps that they kill those insects. So they managed to recalibrate the error, let's say. So yeah, I believe that in terms of philosophy of science, as we said the previous time, it's important to have a discussion also about the history of innovation and technological innovation.
That's for sure. That's for sure, because innovation is amazing. What can be accomplished, and how one idea can have worldwide consequences. It's just amazing.
Yeah, and I think it was Jonathan Pageau who said that it's important to. I forgot about the point. I will write you about it. Okay.
Okay, that sounds good. That sounds good. Well, this has been very, very informative, Haris, and I appreciate so much all the work that you did putting this together, and I hope that there are some other mathematicians out there that will take a look at it and comment, and that you can get some feedback that can help you on your path, because this is the kind of thing that has to be looked at by a lot of people, right, in order to get some traction.
Yeah. I was also giving a thought about, again, back to Glenn, the physicist, what he said about if you can actually think of a solution about a point of disconnection where the computation that takes place in the layer below the quantum doesn't affect let's say, the classical computation. I think I found a way around that. So maybe
that would be a very cool thing to talk about. Great.
Yeah.
Well, this has been very cool talking to you, and I look forward to our next get together, and have a wonderful week.
You too.
Okay. Thank you.
Bye.
Bye.
Take care. Bye.